Okay, let's dive into this. Welcome to today's explainer. We're going to explore the dynamic, completely invisible forces that literally dictate the shape of our physical world. I want you to look at the structures around you, like the ones right here, not as just boring static objects, but as energetic systems in constant motion. Every bridge you drive over, every building you walk into, even the tools you use, they are all secretly fighting off forces that are desperately trying to bend, twist, and shift their shape. So today, we're unlocking exactly how materials actually manage to do that by looking at a foundational concept of physical deformation. It's called the shear modulus.
To really get a grip on this, imagine a solid block. What happens when you push hard against the top of it, but the bottom is just totally stuck to the floor? Well, the top layer wants to slide forward with your push, right? But the bottom layer is held firmly in place by friction. So the entire block is forced to skew. It tilts diagonally as it struggles to handle both the push and the hold at the exact same time. You've actually experienced this yourself. Think about trying to cut a thick wire or maybe a chunk of hair with a pair of incredibly dull scissors. The blades don't cleanly slice. Instead, they just push the material in opposite parallel directions, forcing it to bend and deform rather than snap. That skewing, twisting action, that is shear.
Section 1. The shape of shear.
So let's look at how different materials physically respond to these relentless, shape-changing forces. To do that, we need to define what we're actually measuring. Shear modulus is, simply put, the ratio of shear stress to shear strain. It measures a material's overall rigidity and its direct response to being pushed out of shape. Now, you'll usually see this written as a capital G or sometimes S, or even the Greek letter mu. But the vital takeaway here is the relationship. High values mean a solid is incredibly rigid. You'd need an immense, almost unfathomable amount of force to produce any noticeable deformation. On the flip side, low values mean the material is soft and squishy. It just surrenders and bends to that force right away.
Now, what's really interesting here is that, by definition, fluids have a shear modulus of absolutely zero. Zero! Think about that motion. A fluid simply cannot resist a shear force. I mean, even a light breeze blowing horizontally across a pond instantly ripples the surface, right? That's because the liquid completely lacks the internal rigidity to push back against that sliding motion. Honestly, it's a purely mathematical way to define what actually makes a fluid a fluid.
Section 2. The math of deformation.
Okay, let's see how this equation, G equals tau over gamma, actually plays out in the real world. Think of it like a sequence of moving parts. Step 1, a force applies parallel to the top surface. Just imagine a heavy plate sliding horizontally across the top of that block we talked about. Step 2, an opposing force, like some intense friction, grabs hold of the opposite bottom surface, locking it perfectly in place. And step 3, because the top surface slides and the bottom absolutely doesn't, the entire side of the block stretches and leans. We measure this transverse displacement, which is basically the physical distance the top moved relative to the bottom, or the angle it creates, which we call theta. So your shear modulus is just the mathematical ratio of the stress of your push divided by the strain of that resulting bend.
Let's plug some real-world numbers into this moving system. Imagine we're actively testing a sample in a lab. We apply a shear stress of 4 × 10 to the 4th newtons per square meter. In response to that stress, the material deforms right before our eyes, giving us a measured shear strain of 5 × 10 to the -2. To find the shear modulus, it's pretty straightforward. We just divide that stress by that strain.
And our resulting value comes out to a bold 800 kilopascals. The shear modulus is measured in pascals, which, if you remember, is the standard SI unit of pressure. In this setup, our math gives us 8 × 10 to the 5th pascals, simplifying perfectly to 800 kilopascals. Or, if you're working with English units, you'd calculate this in PSI, pounds per square inch. This final number is awesome because it gives us a concrete mathematical fingerprint of exactly how much that specific block of material is going to resist bending.
Which brings us to Section 3, orientation, heat, and pressure.
So, the crucial point here is that a material's rigidity isn't just some universal static rule. Let's look at how things are built on a microscopic level. We generally classify materials into isotropic versus anisotropic. If a material is isotropic with respect to shear, its deformation is totally uniform. It pushes back with the exact same resistance no matter which direction you apply your sliding force. But anisotropic materials? Totally different story. They are highly susceptible to shear depending on their specific orientation. Think about chopping wood. If you swing an axe and apply force parallel to the wood grain, it splits super easily, right? But turn it perpendicularly against the grain and it fiercely resists. Or take a diamond. Its intricate crystal lattice means how readily it shears entirely depends on the exact angle and orientation of the force hitting those internal carbon bonds.
On top of that internal structure, the physical environment totally matters. As you'd probably expect, turning up the heat or piling on intense pressure makes deformation a whole lot easier, fundamentally decreasing a metal's rigidity. To predict this shifting behavior in real time, engineers rely on a few specific models: the mechanical threshold stress, or MTS model, the Nadal and Lepak, or NP model, and the Steinberg-Cochran-Ginnin, or SCG model. Now, the math behind these is incredibly dense, but what they do is absolutely vital. They help predict how metals behave in extreme real-world conditions. Actually, a quick caveat though. These models work primarily for the linear ranges of temperature and pressure. Once things get too extreme outside those bounds, modeling the behavior gets wildly tricky.
Let's move to Section 4, the Shear Modulus scale.
Let's move on and see how this all builds up. We're going to look at how the materials making up our world actually stack up against each other at room temperature. Take a walk through the spectrum with me. Down at the bottom of our list, representing the softest, most flexible materials, we have rubber, sitting at a tiny 0.0006 gigapascals. It practically begs to change shape under pressure. Moving up, we see synthetic polymers like nylon at 4.1. Then we hit the basic metals, where aluminum sits at an intermediate 25.5. But as we get into transition metals and heavy-duty alloys, the resistance to motion just spikes. Steel stands incredibly strong at 79.3 gigapascals. And finally, standing entirely in a league of its own at the very top is diamond, with a staggering 478.0 gigapascals.
And this brilliantly illustrates just how massive the differences are. Watch how these values scale visually. On one end, rubber's squishiness is so extreme, its level barely registers mathematically compared to the others. Then in the middle, steel shoots up, proudly showing off its industrial, rigid strength. And then, look at diamond. It absolutely rockets off the chart with its near impenetrable resistance to motion. It takes an astronomical amount of directed shear force to make a diamond's crystal lattice even slightly deform.
Now, it's super important to note that shear modulus doesn't just exist in a vacuum. It perfectly mirrors other measures of a solid stiffness, primarily Young's modulus, which measures linear resistance, and the bulk modulus. Together, the whole shebang is known as the moduli of elasticity. They're all deeply connected to each other, uniting under the physics of Hooke's law. Basically, they all tell the same incredible mathematical story: a material's inherent, built-in desire to snap right back to its original perfect shape after being forced into motion.
Which brings us to our final thought for today's explainer. We've seen how dynamic forces bend, twist, and skew everything from soft rubber to hardened steel. But if even a diamond, literally the hardest natural material on our graph, can mathematically and physically deform under the right applied forces, what does that actually mean for the structural limits of our physical world? Is anything truly unbreakable? I want you to carry that thought with you the next time you see a skyscraper swaying in the wind, or a bridge flexing slightly under heavy traffic. Our world is in constant motion, resisting unseen forces every single second of the day. Keep exploring, keep observing, and thank you so much for being a focused learner with us today.